Hello, everybody. So very warm welcome to this session on the probability section of this very unusual ICM. My name is Marta Sansolé, and I am a professor at the University of Barcelona. And it's my great honor to welcome the next speaker today. So it's Professor Laurent Saloff-Coste at Cornell University. And the title of his lecture is Breaking Heat Kernel Estimates into Pieces. So please, Professor Saloff-Coste.
Thank you, Maria. Thank you, everyone, for coming to the talk and listening. I'm going to talk about heat kernel estimates. And I hope to convey the interest in this subject during the lecture. What I'm going to talk about is in very, very large part joint work with Alexander Grigoryan from Bielefeld University. Grigoryan and I have been working on this heat kernel estimates over the past 25 years at least together. It's also joint work with Satoshi Ishiwata from Yagamata University in Japan, and with Pavel Giria, who has left mathematics and works in data science, and with Emily Dottenham, who is current Cornell graduate students working with me. So let's start with the heat kernel. And on this picture, we have 4 instances of a Gauss curve. One is very flat, and maybe it doesn't look so much like Gauss curve, but it's a Gauss curve with a very large variance. In terms of the heat kernel, the variance is related to the time. So the curve that we see here is the one that probably looks most like a Gauss curve. And it is peaked at 0 because we have centered this Gauss curve at 0. It has a certain width which corresponds to the variance or to the square root of time, or the time. And then the main thing we can observe on this picture is the very fast decay of this function when we move towards infinity. And of course, it's symmetric. So this, I said, are 4 instances of Gauss curve, but you can also see it as 4 instances of the heat kernel at different time on R. So this picture should serve as a model for the heat kernel. It tells us how it looks in the simplest possible case. Now, here is the formula for the heat kernel in Rn. So now we have in Euclidean space Rn. We can take this picture and rotate them to have a cartoon idea of what the Gauss curve in the plane looks like. It would have to be adjusted because there is a change in this term depending on dimension. So this is a formula of, if you want, Gauss curve of Gauss map in Rn. And people who study the heat kernel have devised a way to talk about this formula that breaks it into two pieces. When x equal y, so on the diagonal, the exponential term here is 1. And what's left is this term, which is t to the minus n over 2, if we ignore the constant, and give what we call the on-diagonal behavior of the kernel. It corresponds to the maximum of the kernel when x equal y equals 0, for instance. At all time, the maximum is at 0. And the second part of this formula, this term, is called the Gaussian term. And it captures the very fast decay of the kernel at infinity. The smaller the time, the faster the decay of this kernel. And of course, it dominates the width of the picture of this kernel here. So this term is comparable to a constant whenever t is of order the distance between x and y squared. When that's the case, the main component of the behavior of the kernel is the other term. This kernel represents the evolution of the distribution of heat in a piece of homogeneous metal, iron or something. And it is known as the fundamental solution of the heat equation. And the heat equation is the simplest parabolic equation. It's written here. We take the partial derivative in time, subtract the Laplacian, which is the sum of the square of the partial derivative in each coordinate direction. And we apply this to a function u, and this function u is a solution of our equation if the result is 0. So the word fundamental solution refers to the fact that the initial data for the particular solution that is represented here is a Dirac mass at x in the case of this formula. So the equation is a basic model for all parabolic equations. It has very specific property because delta is a second order differential operator. And we are going to use this in this talk, of course. Our goal is to understand similar object when the underlying space is more complicated, different, more general than Rn. So in this marginal context, we need some notation. We are not going to use much of it so much today, but still. So the main object we want to study is the heat kernel, which is a function of t and two space variable x and y. These space variables, they belong to some domain M, which replace Rn. And I will give you some example. In this talk, we'll stick with very simple instance of M. I will talk about that in a minute. This M has some structure, and so we can define some Laplacian. using this Laplacian, which is an operator, we, one way or another, construct the exponential of t times this operator. And this is what we call the Heat semigroup. It is a semigroup in the variable t. And it acts on function. You can think of smooth, compactly supported function or any nice class of functions that you prefer. The Heat semigroup, in a sense, is the easier object to construct. It is a rather soft object. It can be typically constructed using functional analysis, and we don't need much detailed hypothesis to make sense of it. And so we can think of it as a first thing to construct in this concept. But when things go well, this semigroup, the action of this semigroup on function is given by a simple integral, which I have written here, and which involve an object, which is the object we want to study, and we call it the Heat kernel. So this is a transition kernel that tells us how to go from x to y in time t in some sense that I will make more precise later. But right now, it's just an object that allows us to compute the semigroup using an integral formula. There is a reference measure here, which is associated or related in some way to the Laplacian that we are using, because in this talk, the Heat semigroup will and the Heat kernel will be symmetric object in x and y. So somehow we have the symmetric property that this formula holds. And this has to do with a relation with the reference measure and the upper delta. Essentially, it has to do with integration by parts. So what are the domain M that are of interest to us? Well, for instance, M could be a connected domain in Rn. Instead of all of Rn, it's only a piece of Rn. And if we have this nice piece, nice domain omega, one new thing compared to Rn is that we need to specify some boundary condition in order to make sense of this semigroup and this Heat kernel. And for us today, there is two boundary conditions of importance, which are the two main boundary conditions considered in general. The Neumann boundary condition, which correspond to asking that the normal to the boundary of any solution vanishes. And a different boundary condition is a Dirichlet boundary condition where we ask for any solution to itself vanish at the boundary. The case of Neumann boundary condition in a domain for us, we can think of it as a case where there is really no boundary except that in our description of the problem, there is a boundary, but the point of the boundary are really part of our space and nothing very special happen at those points. This is very different from when one imposes Dirichlet boundary condition, where the fact that we require the solution to be zero there means that there is something very special happening at this boundary. And these two things will play a role in this talk, so we'll come back to them. So another case of interest is a complete Riemannian manifold. So I have tried to draw here an example of such. Of course, I've drawn a surface because it's hard to draw anything else. And this surface is quite typical of the object that we want to study in this talk. So we'll see it again and again. So in this context here, there is a metric on our manifold. That's why I call it a Riemannian manifold. So we are able to compute lengths. In this drawing, the surface is embedded in R3, and that's what the drawing is showing us. And that embedding provides a metric on that surface. And so we can measure the length of curve going between 2 points on the surface. And so this gives us a notion of a gradient. The gradient is a way to see the differential of a function views the length through the length of the metric. The same way that we have a correspondence between forms and vector in Euclidean space. And there is a more, slightly more complex operator called the divergence, which applies to gradient and compose with gradient. And together they give us the Laplace-Beltrami operator, which is a Laplacian that we want to study in this case. So this is a very classical object. And it's an interesting differential operator in a Riemannian manifold. So it is defined independently of a choice of coordinate on this of patches on this Riemannian manifold. I want to talk for a minute about the slightly more general setup, which is the setup of weighted manifold. And the only thing that changed compared to a Riemannian manifold, so let's start with a Riemannian manifold, like in the previous example, we have the manifold M and the metric G. And from that, we compute the gradient of a function. We also have a volume that give us a measure, a canonical Riemannian measure on this manifold. And these two things together give us the Laplacian in this case, which is what I explained before. Now, suppose we add a weight. So we are given now additional data, a weight which I call sigma here. It's a positive smooth function on M. Then I can consider this object, which we can call the energy, or a more precise name is the Dirichlet form. We take the gradient of a function, we compute the length of this gradient. The gradient is a vector field, so we can compute the length of that gradient, square it. And instead of integrating this gradient square against dV, which is our basic volume, we insert the weight sigma in this formula here. So this gives it what we call the weighted manifold, and it defines a Laplacian. So now this Laplacian here in the orange box could wear a subscript sigma because it depends on sigma. If you look at this formula and try to integrate by part one of the gradient to obtain the next line, then of course the computation will involve sigma. And so the orange box represents the definition of the Laplacian for a weighted manifold. So in all these cases, we have a heat equation, and we want to try to understand the heat kernel associated with this heat equation. Now, I didn't talk about why we are trying to understand the heat kernel, but there are many reasons for that. One of them is related to Brownian motion and probability. So Brownian motion is a stochastic process So in this case, xt, we should think of it as a continuous curve parameterized by t. And there is a probability measure on the space of all these continuous curves, which allow us to compute the expectation of a function viewed at the point xt, where the random curve is at time t. This x means that we start at the point x. And this particular process, Brownian motion, is such that computing this expectation is exactly the same as computing the semigroup, the heat semigroup applied to the function f at time t at the point x. And so this is a formula that relates this heat semigroup to the heat kernel, which I showed a few slides ago. So if we take our Riemannian manifold here, in red, I have a attempt to a picture of Brownian motion wandering around on this manifold. And at a given time t, the position of this random process is what's involved in this formula. And so understanding the heat kernel is the same as understanding what happened to this Brownian particle on this Riemannian manifold. The Brownian motion is reflected at the boundary if we consider a Neumann condition, and it is killed at the boundary if we consider the Dirichlet boundary condition in the heat equation. So now, what is our goal? Our goal is to find a situation where we can obtain two-sided estimate of PTXY, so the heat kernel, which are, these estimates should hold for all t and x and y in M. So they are very global. In particular, I'm interested in large time and global aspect of this equation and of the heat kernel, not, for instance, about, in the asymptotic when t goes to 0, which is an interesting problem, but a different one. And so there are many cases where this is very difficult to do, and many cases where we still have no idea how to do that. But the question is, are there, what are the situations where this goal is attainable, and what are the techniques that would allow us to do that? And by two-sided estimate, I mean two-sided estimate that looks the same on both sides, so that from the existence of these two-sided estimates, it is pretty clear in itself that we have a good understanding of the heat kernel PTXY. There is one more thing to say. So what does it mean to have this two-sided estimate? So for instance, for any ball B anywhere, we should be able to estimate the probability that Brownian motion started at x and at time t in the ball B. And this is just the integral of the heat kernel in y over the ball B. And so if we have good estimates for the heat kernel that are two-sided, we should be able to get a good estimate of this probability. Let's think of the heat kernel as representing the temperature, given that we put a very infinite amount of temperature at the point x at time 0, and then we let it diffuse in our body. Then we may be interested is at what is the maximal temperature anywhere in space. So this is this function of t. We take the maximum in y of the heat kernel. X is our starting point, T is the time we are interested in the behavior of the maximum. But we also may be interested to find the location of those Y where this maximum is attained. So suppose my point X is here. Now, I wait a million years. Where is the maximum temperature in my body, in this case, the surface that is drawn on our page? So that's the kind of question we would like to be able to answer. Now, the main principle I want to explain today is breaking things into pieces and gluing them back together. And so this main principle has two steps. The first step is identifying good pieces where we already know the kernel. So these pieces should be things that we feel very comfortable we understand. And step two is to reconstruct the global kernel on our object by gluing back what we know for the different pieces that form our object. This step two is rather complicated because it requires the understanding of interaction between the pieces. But in order to implement this scheme, we need to decide what is a good piece. Anyway, let me give you an example of this scheme. So the first example is, there is only one piece. So what we need to know is what are good pieces? What are pieces that we can study without breaking them? I'll answer that question in a minute. Another implementation of this scheme is, let's think of the pieces as single points. Of course, we understand everything about a single point, but it's not very interesting. And then, of course, this scheme reduced to understanding the interactions between all these single points. And this is hard. It's the same as the first question. We haven't done nothing. But I think it's really useful to keep in mind that we can think of a manifold as a whole, one object, or as this incredible complicated collection of points. And what we want is to live in between and use this idea. So one classical way this is implemented is discretization. So here is my object. It's a surface, periodic surface made of infinitely equal pieces that are described here. I think the picture make it clear. Now these pieces, they are compact and simple and they're all the same, so we understand them pretty well. And so if we break our surface into this infinite collection of little pieces, the whole difficulty to understand the kernel is to understand the interaction, and it's a problem of a discrete nature. We are not interested in this particular implementation here. This is something that has been done, but there are still many open questions in how to obtain good discretization in that spirit here. So the main example I want to talk about today are those two examples. And on the left here, we have the catenoid, which for our purpose is really very similar to the connected sum of two planes. Now, this is made of two very good pieces. One is the top plane, if you want, and the other is the bottom plane. can we glue back together what we know about these two planes in order to understand the heat kernel on the catenoid? On the right, I have a three-dimensional solid body. So this picture is a piece of metal, if you want, in free space. It's not the surface. And this piece is made of a conic part here, infinite, a planar disk, infinite, that goes, and a long cylinder, infinite, going down. So this is a domain in R3, if you wish. So we are going to consider the heat kernel with Neumann boundary condition in this domain. And we can recognize immediately that this is made of three pieces that we understand quite well. This conic part, the planar slab, and of course the cylinder, half cylinder. So what is a good piece? In the previous example, I recognize a good piece is because they just look good. So a good piece for us is what I call an Harnack manifold. And these are manifolds which have two key properties. The first thing is that in these good pieces, the volume is doubling. So if we compute the measure of the volume of a ball of radius 2r, it's controlled by the volume of the ball of radius r, independent of scale and location. And the other key property is the Poincare inequality, which is a more complicated inequality. It controls the variance of a function in a given ball in terms of the integral of the gradient square in the same ball. And the control is in terms of the radius of the ball with a very specific scaling of r squared. And we want this property to hold at all places and location. What are examples of good pieces? Well, Rn itself is a good pieces. Convex sets in Rn are good pieces. Non-negative Ricci curvature manifold, Riemannian manifold are good pieces, and this was proved by Peter Buser, who obtained the Poincare inequality, and Chigger, Gromov, and Taylor, who proved doubling. This is the doubling in this case is a result of the well-known Bishop-Gromov comparison theorem in Riemannian geometry. There are many other examples, but I will stick with those for today. And so these are the good pieces. And there are good pieces. So in these two examples that we had before, this part has this properties, a planar stab here has this property, the half cylinder has this property. In the catenoid, if we cut top and the bottom, then each of them have all these properties. In these two cases, the entire manifold here does not have doubling of the volume. This example does have doubling at all scale and location, but it fails the Poincare inequality. This is a little subtle, but it's a property of balls that include connect the two ends of this manifold. So these are good pieces because of a theorem by Alexander Grigorian and myself. We prove it independently in the early 90s. And it says that if we have these two properties I mentioned, volume and Poincare, then we have a very good control of the heat kernel. This heat kernel is controlled by the volume of ball and a Gaussian term, which looks like the usual Gaussian term in Rn. And so on this manifold, the kernel looks like this, which is reminiscent to the picture I showed you at the very beginning. So a good piece for us is an Harnack manifold with these properties. So in this example, each of the pieces I described before have this property. So what do we need to know about these good pieces? We already know a lot. They are Harnack manifold, so we have a good kernel bound for these pieces. And when I mean pieces, you know, here I have drawn the cone to which I have added a little bottom to separate it from the picture I had before. So in addition to the kernel, we need to be able to control hitting probability. So what is that? This is a probability that starting at X, we hit the place where we cut these pieces before time t. So tau here is a random time. It's a random time at which Brownian motion hits the cut. Each piece has a cut. Here on this picture, we start at X. Brownian motion runs until it hits the cut. My picture is not so good. The Brownian motion, of course, could go this way first before hitting the cut. And so we need to estimate what is the probability that starting at X, we hit the cut before time t in each of these pieces. And this is a very interesting problem, the solution of which depends on computing what I call the harmonic profile of the piece, which is an harmonic function, so a solution of delta H equals 0, which is positive, and 0 at the boundary, at the cut. In this picture, in this case, H is not very interesting. It is constant at infinity, and this has to do with the fact that this cone is something of dimension free, and so it has to do with the transience of Brownian motion in dimension free. If we stick with this example, the function H, this profile for the other pieces is more interesting. So in this planar slab, the function H behave like log of the distance to the central cut. And in the half cylinder, the function H behave like also just the distance itself to the central cut. So in general, we need to compute this function H in order to understand this hitting probability. And this is a rather difficult problem, actually, where still a lot of work has to be done. In addition to that, we need to understand the hit kernel with Dirichlet boundary, zero boundary condition at the cut. So here I add this omega to say that this is a Dirichlet boundary condition hit kernel. And in the case of this cone, a three-dimensional cone, this hit kernel is actually just similar to the hit kernel of the piece. This again has to do with the transience of Brownian motion in this cone. But in the other two pieces, we have a thing that looks much more interesting, and the formula start to look quite complicated. The important point here I want to do to make is that this formula involve very precisely and very importantly the function H, the harmonic profile. So for this first example here, the function H is just this function. And for this example here, the function H, the harmonic profile, is just this function. So when we have all this, we have all the knowledge we want on the different pieces, and we need to glue them back together. So we want to understand what is the probability that Brownian motion starting at x end up near y at time t. And we want to try to understand that by gluing back together what we know about the different pieces. But knowing about the different pieces in themselves is not enough. We need one more ingredient, and which is how this thing connect together, the interaction between these pieces. And this is captured by just the behavior of the heat kernel at a central point O. So on this picture, here is a central point O. It's somewhere in the compact middle of our manifold. And we need to understand what is the probability that if we start at O at time 0, we are back at O at time t. Now, in this example, I have used cuts that are through a compact part, but we may want to make cuts that are non-compact, like on this picture. And in this case, what we need to understand is the heat kernel between any 2 points that are situated on the cut that separate the different pieces we want to consider. So now, what is the final product of this investigation? It's global two-sided estimate for the heat kernel. And I'm going to show you on our example. So the first example I want to take is not quite the catenoid, it's the 2 copy of Rn glued together, but n is bigger than 2. In this case, I can show you the formula for the function that controls the heat kernel. It contains a distance. This plus means that this is a distance between x and y passing through this part. This empty space here means it's a distance between x and y avoiding the middle. This means that this distance is infinite if x and y are in 2 different sheets. These functions here are just the distance of x or y to the central part. Let's look at my main example, which is this solid piece of metal in R3, and fix one of the points to be at the center here. So that's how is going to be my point O. Consider 3 different points, X, which is in the 3-dimensional cone, Y in the slab, and Z in this cylinder. What is the temperature at this point if we start with all the temperature, all the energy concentrated at 0 at time 0? And we can answer this question by this technique. So at 0, what is the probability that what is the size of the temperature at the point O at time t? It is this interesting function of t. What is the, where is the maximum of the temperature at time t? Well, it is at this point Z, which is in the cylinder at the bottom, where everything is scaled at distance square root of t. So the point Z is at distance square root of t down the cylinder from O. And this is the maximum value of the kernel. I'm going to stop here and thank you for your attention.
Thank you very much, Professor Saloff-Coste, for this very clear, excellent, very interesting lecture. And thank a lot also to all the audience. So unfortunately, there is no possibility of questions and answers, but well, that's life in this strange ICM. So have a nice afternoon, and thanks again. So bye-bye, we close this session. Bye-bye.